Welcome back to another exciting adventure in trigonometry. Today we're going to take a look at trig ratios and special angles, which I believe you did in the previous course, whether that was the 11U or 12CT, MCT, whichever. But I believe you have taken a look at these. But we're going to go over them again, and we're going to expand on them a little bit so that we can do a whole bunch of other angles as opposed to just a few basic ones. So without further ado, let's take a look. Okay, I'm going to start off just by reminding you of hopefully something that you have not all forgotten, and that is this wonderful word, SOHCAHTOA. If that word looks new to you, I wonder how you got to this course, but anyway, that stands for sine of an angle is equal to the opposite over hypotenuse, cos of an angle is the adjacent over hypotenuse, and tan of an angle is equal to opposite over adjacent. And we're going to use that idea along with a couple of special triangles in order to figure out some exact values for angles. So the two triangles we're going to use are in this diagram here. We have one that has a 30 degree and a 60 degree angle, and one that has two 45 degree angles. Both of them are right angle triangles. Now I'm just going to try and highlight a few things here. So on the 45 degree one, this one's pretty straightforward. We could just call each of the sides 1 unit long, and that's basically half a square. If they're equal in length, then we have two equal angles there, 45 and 45, and the third side must be root 2 by Pythagorean theorem. Hopefully you also recall Pythagorean theorem. Now that doesn't mean that that's the only triangle that works. We could have multiplied and had this as a 2 and this as a 2, and that would be 2 root 2, but this is the simplest triangle we can make with the 45 degree angles in it. Similarly, and this one's a little bit less obvious, but over here we have a 60 degree angle and a 30 degree angle. And if you want to know where these numbers came from, technically they came from a triangle that was equilateral and had 60 degrees in each side, and we labeled each side as 2 and then cut it in half and ignored one of the sides. So that's how we get 2 units for the length of the long side, 1 unit because that's half as long because we cut it in half up here, and then the remaining side, root 3, is just the Pythagorean theorem result when you find out the missing side. And because we cut it in half, we also have the 30 degree angle up there instead of a second 60 degree angle, obviously. All right, just for one moment, I am actually going to skip over the very first question it asks us to find, which is the exact values for 0 degrees or 0 radians. And by the way, I put down the radian values here, but I'll refer to everything in degrees for the most part. So if we want to find the exact value for the sine of 30 degrees, first of all, we look over, we find 30 degrees. It's right here. And the sine of that angle, according to SOHCAHTOA, is opposite over hypotenuse. And that's going to be 1 over 2. And I put it in the wrong spot right off the bat. And that's why pencils come with erasers, or digital things come with digital erasers. So 1 over 2. The cos of 30 degrees is going to be the adjacent over the hypotenuse. So in this case, the root 3 over 2. And I'm realizing now, and I actually realized this before I started, that I'm going to be drawing on these triangles a lot. So I'm going to stop underlining stuff as I talk about it, and you'll just have to kind of look along with it. Tangent of 30 degrees is opposite over adjacent. Opposite is 1. Adjacent is the root 3. Okay, that wasn't too painful. 45 degrees, we can do the same trick. I'll look down at this bottom corner, although it doesn't really matter. But the sine of that is going to be opposite over hypotenuse, which is 1 over root 2. The cos is going to be adjacent over hypotenuse, which is also 1 over root 2. And the tangent is going to be opposite over adjacent, which is 1 over 1, which is 1. 60 degree angle, going back to our first triangle, 60 degree angle Opposite over hypotenuse is root 3 over 2. Adjacent over hypotenuse is 1 over 2. And opposite over adjacent is root 3 over 1, which is just root 3. And I'm just going to make a quick note there that these two values are just the reversal of those two values. And this are just reciprocals of each other. Just as a little note. Now let's go back and answer the first part, the last part. What would the sine of 0 degrees be and the cos of 0, the tan of 0? Well, here's what I want you to think about. If I look at 0 degrees, think about a really, 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 really long, skinny triangle. Right-angled triangle. And we're going to say that it's so skinny, so long and skinny, that this side and this side are both the same length. The hypotenuse is the same length, and that the side is effectively 0. And that's essentially what will be true when the angle inside, the angle over here, is 0 degrees. There is actually a thing in mathematics called the long skinny triangle theorem, which basically says this, that if you have a triangle that's long and skinny enough, the hypotenuse and the longest side are essentially parallel, and the distance between them is 0. Okay, if we make that assumption, we're dealing with a long skinny triangle, the sine would be opposite over hypotenuse. Well, the opposite is 0. The cos would be adjacent over hypotenuse, which seem to be the same length. So they're 1. And the tangent is opposite over adjacent, which is again 0. Now if we use that same logic for a triangle that's almost 90 degrees, so this angle down here is almost 90, and we label the three sides as 110, then the sine, the opposite over the hypotenuse, opposite over hypotenuse is essentially 1. Adjacent over hypotenuse is 0 over 1. And opposite over adjacent is 1 over 0, and that's undefined. Okay, so that's all of our special angles between 0 and 90 degrees. 0, 30, 45, 60, and 90. That covers all of them. And what we want to do is be able to expand that to a whole bunch of other angles within this circle. So now we're going to introduce something called the related acute angles, which I refer to as the bow tie diagram. And I think that bow tie diagram, or that diagram right there, will show you why I call it the bow tie diagram. I want you to think about this as being a beautiful bow tie. I think you might wear it to a formal event, except yours probably wouldn't be pastel yellow. Okay, the reason it's called, or I call it the bow tie diagram, is because of the shape. The reason they're called related acute angles is because if we take an acute angle, and what I'm going to do is focus on one particular triangle in the first quadrant here. There's a 90-degree triangle, a right-angled triangle. And I'm just going to say, okay, let's pretend that that's theta. I guess we're not pretending. I guess we're defining. So we can do whatever we want. If that's theta, then I'm going to actually just label it out here as well, just to show that by the time we've gone this far around the circle, we've gone theta degrees, or theta radians, whichever angle measurement we want to use. If we know anything about that triangle, and we do if it's one of our special triangles, if it's the 30, 60, or 45-degree triangles, then we also know everything about the three other triangles that are actually appearing in here. So as an example, we know a lot about this triangle because it's exactly the same shape. And this triangle down here, and this triangle over here. If they're all the exact same special triangle, we know lots about them. So that means that if we know information about angle theta, and again, we only know it for the 30, 45, and 60, but if we knew it for any angle, we would know it for this angle as well. Well, that's going to be 180 degrees minus theta. Or if you want to do it in radians, I did not want that. This would be pi minus theta. If we want to do it for this angle here, well, that's going to be 180 degrees plus theta, which we could also write as pi plus theta if we're working in radians. And finally, this angle over here is going to be 2 pi minus theta, or 360 minus theta, if we want to work in there. So anyway, we've got 4 different angles now that we know everything about if we know what the exact value of angle theta is. We're going to add to that this idea of the cast rule. I'm just going to remind you that for labeling quadrants, this is actually quadrant 1, 2, 3, and 4. And for reasons I'm still not sure about, we always use Roman numerals to show the quadrants. I'm guessing it's just so it doesn't get mixed up with the x and y values on an axis if we're drawing them on top of an axis. But the cast rule says that when we're in quadrant 1, by the way, the cast rule starts in quadrant 4 and works up this way and across and down and over. And now that I've written that, I don't like it there, so I'm going to erase it again. But we start in quadrant 4 for the cast rule for some reason. Well, actually, I know exactly why we start in quadrant 4. Because if we start in quadrant 1, it would be the asked-C rule, which doesn't sound as good. So now that we have the cast rule, we can say that anything in quadrant 1 is going to be positive. That's what the A stands for, is all of them are positive. The sine, cos, and tangent. If our angle is in quadrant 2, the S says only the sine will be positive, the cos and tan will be negative. In quadrant 3, only tan will be positive, sine and cos will be negative. And in quadrant 4, only cos will be positive, sine and tan will be negative. And that's going to help us actually solve some pretty straightforward stuff if we can remember those ideas. All right. So going here, we're gonna do each of the 3 special triangles. I realize technically the 30 and 61 are the same triangle, but bear with me. We're going to treat them as 3 separate triangles, and we're going to figure out exact values of the 4 related acute angles. So again, we're always going to focus on the triangle over here in quadrant 1. That's the one that matters to us. Okay, so if we do this, we can put 30 degrees in there. And again, I'm just going to label it out here as well to remind you that that's the angle starting here and going counterclockwise. And if that's the 30-degree angle, our special angle said that this is going to be a 2, this is a 1, and this is a root 3. So now our related acute angles will be over here at 180 minus 30, which is 150 degrees. Down here at 180 plus 30 is 210 degrees. And over here, 360 minus 30 is 330 degrees. Now the interesting thing is the sine of the first one, the sine of the 30-degree angle, we've already done this one, but I just really quickly put it in, is opposite over hypotenuse is 1/2. Cos is adjacent over hypotenuse, which is root 3 over 2. And tangent is opposite over adjacent, which is 1 over root 3. So now when we look at the others, let me just change color for a second. Let me try and change color for a second. Hey, there we are. Now when I look at this triangle, the 150-degree equivalent, and I realize the angle in here is still 30, but we can still use that triangle for the 150. The only thing that's going to be different is that there's going to be some sign differences, or it could possibly be some sign differences, but that's what cast is for. So for the 150, we can conclude, switch back to here, that we should have the exact same ratios. 1/2 root 3 over 2 and 1 over root 3, because we're dealing with the exact same shaped triangle as we were in quadrant 1. The difference is, now that we are in quadrant 2, the cast rule says only the sign will be positive. So I put a negative in front there and a negative in front there. And by the way, if you don't believe me on any of these, you're welcome to punch into your calculator and verify that they do work. You will have to convert these to decimal numbers and you'll get your answer in decimal numbers, but you can verify that they work. And if we want to do the one for 210, same triangle as the others, so we're still going to get the same angles, or the same lengths, I should say. 1/2 root 3 over 2, 1 over root 3. But in this quadrant, only tangent will be positive, so this will be negative, and this will be negative. And then lo and behold, the 330, 1 over 2, root 3 over 2, 1 over root 3. And all we have to do is look at the cast rule and say in that quadrant only the cos is positive, so those two are negative. So we found the exact trig ratios for a whole lot of different angles here. And we can continue to do that for the other two special triangles. Now I'm going to run through these ones just a little bit faster because, frankly, I think we can afford to. But they're the exact same idea. So I'll start by putting the 45-degree angle in the first quadrant. This would be 45. This one here would be 180 minus 45. Down in the bottom left, we have 180 plus 45. And over in the bottom right, we have 360 minus 45 is 315. Okay, so now for the 45-degree angle, the one we already know, we have 1 over root 2, 1 over root 2, and 1. And these are going to be the same all the way down because they're all the same triangle, just in a different position. The only thing that's going to change is the signs, and that's what the cast rule tells us. So 135 is in the CAS, sign is positive, the other twos are negative. Here, let me put them here just to make it a little easier to see. The 225 in quadrant 3 is going to be tan positive, the others negative. And the 315 in quadrant 4 is going to be cos positive and sine and tan negative. All right. One more time, if you want to pause this one and try it on your own, you're more than welcome to. If not, that's fine too. We have our 60 degrees there. That would make this one 60, this one 120. This one down here would be 210. Oh, wait a second. That should be 180, 240. And this should be 300. Okay, so just a slight typo in here. I'll fix this on the... I think the radian angles are correct. I think I just didn't change the cut and pasted degree angles. 240. 4 pi over 3. Yeah, that's correct. So the radian angles are correct in there. Your handout, I'll make sure I fix that before I post it. But for now, I'm not redoing the video because I had a typo there. Okay, for the original 60-degree angle, sine is opposite over hypotenuse. That's root 3 over 2. Cos is 1 over 2, adjacent over hypotenuse. Tan is opposite over adjacent. That's root 3 over 1, which is root 3. And since all 4 triangles in the bow tie are the same shape, these are all going to be the same going down. And all we have to do then is make sure that we use our cast rule to figure out what's positive where and what's negative where. For the 120 degrees, only sine is positive. For 240, only tan is positive. And for 300, only cos is positive. And there we go. We've just found a huge number of exact values for all kinds. And now I could, and I have seen diagrams that superimpose all three of these bow ties on the same graph. I think you can see why I chose to do them separately. It is a little bit of a waste of space, but it's digital space, so that's okay. It makes a very big mess unless you have like a full sheet of paper to do all of them on. It gets super, super busy. All right, let's see if we can do a word problem here. And I will ask that you at least read through the question and kind of think about how you would approach it before I do it, because it's always easy to watch someone else do it and say, yeah, that makes sense. In much the same way that I often take my car to the mechanic and watch him, fix it, and then just assume that I'm a mechanic now. And it turns out that watching someone do it and participating in how to do it are two different things. So take a look at this question, think about it, try it, and then when you think you've got something, or you're as far as you can get, I mean, if you want to try and solve it completely, go nuts. When you think you've got it, come back, unpause, and take a look. So I will give you 1 second to pause the video, starting now. Okay, I'm going to continue assuming that you actually tried the problem, knowing full out you probably didn't. Anyway, let's start by trying to figure out what the question is asking, maybe draw a picture, that's always helpful with word problems, and go from there. So you're flying a kite with a string that's 50 meters long. The sun is directly overhead, and the string has an angle of elevation of 30 degrees. Angle of elevation means angle upwards from the ground, just as a reminder. The wind picks up and increases the angle of elevation to 60 degrees. Okay, so what that means is you're here on the ground. That doesn't look like you. This looks like you. You're a stick person. You're flying the kite. It is an angle of 30 degrees above the ground. Oh, wait, that should be a kite, not a circle. And then the wind picks up and takes it up to 60 degrees. So this is 30. This is 60. Okay, and we have a shadow on the ground, which, for reasons I can't explain, the shadow is going to be red. And the shadow on the ground was this long at first, but now it's only this long. So what we want is actually the difference between them, which is this. And we want to know the horizontal distance that the kite's shadow moved as an exact value. So that's what we want. Whew, that seems like a lot. But we can use our excellent skills from today to figure this out. So I'm going to go back and just draw the original picture here and say, okay, wait, our first kite position was a right angled triangle, looked like that. And this was 30 degrees. Now, I know that this up here is 50. But I also know that the ratio of the three sides in a 30 degree angle, the special triangle, is 2, 1, and root 3. So that's the ratio. What are the actual side lengths? Well, one side length is 50, we know that. Well, that's 25 times bigger than 2. So this must be 25 times bigger than 1, and this must be 25 times bigger than root 3. So that's this length. This distance here is 25 root 3. All right. Now all of a sudden the kite goes up to a 60 degree angle. And I know that this is 50 meters again. That's how long the string is. But again, I know the ratio of the three sides is 2 to 1 to root 3. Special triangle. And again, the ratio is going to be 25 times larger. The ratio from 2 to 50. So this is going to be 25 root 3. And this side's going to be 25. Which means this distance is 25. And that means this distance, we'll call it x. X is equal to 25 root 3 minus 25. Now, it's asking for an exact value for part A. I can make that debatably prettier by writing it as 25 times root 3 minus 1, although I don't know that that's really any better. But either way, that is my answer for part A. Therefore, the kite's shadow, I don't know why I put a comma there, moved 25 root 3 minus 1 meters, period. Okay, first of all, this is not the kind of question anyone asks anywhere at Playground, but if it was, and you gave them the answer of 25 root 3 minus 1 meters, be ashamed of yourself. So this is an example where, yes, it is great mathematically that we can find an exact angle, but for B, we want to actually calculate what 25 root 3 minus 1 is, and that's where we take just a brief moment, pull out our calculators. I type in root 3 minus 1 to get 0.7 something, multiply it by 25, and my answer to 1 decimal place is 18.3. And my answer to that one will be, therefore, the kite's shadow moved 18.3 meters. A much better answer. Now, you can keep more significant digits if you want. You can keep a lot of significant digits, specifically because we're getting it from an exact value. We know that that's precise. So as many significant digits as we want works. We don't know the significance of the 30 and the 60 if they're exactly on, but if we assume they are, then yeah, this would be an exact value. That said, we have answered a pretty, I don't know, intricate word problem, I would say. And because of that, I think we deserve a reward. And your reward is some wonderful homework. So there are some homework questions right there. I will put a reminder in for you that the textbook will talk about some of the inverse trig ratios, cosecant, secant, and cotangent. And just while I'm talking about this, I'm going to switch back, just so you can see my face one more time before we leave for the day. Not that you need to. No one needs to see this face. But the inverse trig ratios, I feel bad saying this to a math teacher, but they're completely useless. I hate them. I hate them so badly. I've hated them since university. I've never found a use for them. That said, you need to know how to do them, or at least know how to get away from them. So the inverse trig functions, all you have to do is, the reciprocal trig functions, the secondary trig functions, is flip them and get back to either sine, cos, or tan and work from there. They're not hard to work with once they're sine, cos, and tan, so do it that way. Anyway, I'm going to stop there for today, and we will see you in the next lesson. If you've got questions about this, bring them to me, and we shall look at them. See you later.